Okay, while people come in, I'll get going. So we're still working until the end, we're just going to work on your project and certain things that I want to see in your project. Just so that we can all work together if you want to work with me today, but you can work on your own data sets as well. If you go to electronic reserves, you are going to see the data files. And just to make it easy, I did put this data file there for you, the one that I'm using, that I used a week ago, so you can do the same thing. So there it is, hard_failure.csv. So if you wanted to download it, it's there in the electronic reserves. Okay. And so this is where we were with our project, and I want to continue with that. And so we had our title for our project, all in a Jupyter notebook. Okay, by show of hands though, who's just using Miniconda for the Python environment? Who's using VENV? And who's using UV? So there's a couple of UV as well. Okay, it's a good spread. It's better spread than I have in the formal postgrad Python course. Like everyone there is doing Miniconda. I'm trying to get some of them to use UV or VENV so that everything is tied into your folder. But anyway, so I'm using Anaconda there, or Miniconda. So I've got my Conda environment, remember? So we've got our title. Let's close this to give ourselves a little bit more space. So we've got our title project there. And I think I've changed this one around a little bit when I just redid it yesterday. So at the top, I've got my Python packages, remember? So if I just open that up, I've got my normal things, NumPy, SciPy, Pandas, Seaborn, and Matplotlib. And I'm setting the plotting environment to high-resolution displays. Make things easy as well. Let's just go here. And let's go for themes. Let's change my color theme. And let's just go for that's better. So we can see the screen a little bit better. Okay, so those are the usual things. Do remember that what I don't have here are all these markdown cells. I want a markdown cell there, and you tell me a little bit about what's going on in every section. And every time you get a result in the results section, I want to see some markdown just explaining what the code is showing you. Okay, and so I'm not putting any of these in because I'm just demonstrating here for you. We had our introduction. And we knew I used Perplexity, showed you Perplexity. And so who's done that? Who's got their introduction written? Most people. Who's got their background written? Okay, again, most people. That's cool. Then my methods, we'll just use that and leave that till the end. What I've done when I recreated this yesterday, I put my data import and verification inside of the methods section. I don't know why I did it yesterday. Does anyone know how to change the focus on this thing? Or is it just me? Seems out of focus. Does that seem okay to you? Okay. It really seems out of focus to me. But anyway, so this time I put it in methods, data import and verification. So we've done that. So if you want to play along, let's do that hard_CSV. So if I look inside of I'm doing a very old-fashioned thing. I'm not using API to get the data straight from the internet. I've got my hard_failure CSV file right in the same project. So when I reference the file, it comes, I don't have to say, where it is on my hard drive or anything like that. I've got my shape. So let's just run all. So I've got my, is it running? Yeah, so I've got everything there. And I've printed out the first couple of rows. We saw all of this. A week ago or so, we also did the exploratory data analysis. And the first one we started with a death. We saw that the unique values were yes and no. And you absolutely have to do this for the variables that you're going to use in your project, because as I say, you don't want to get to a point there where someone was typing NO with a capital N, NO with a lowercase n, uppercase n, lowercase n, and then it's different unique values. And when you analyze your data, that's going to be all wrong. So you want to catch those things. Then we did our frequency. Then we did the relative frequency. So we saw that 67% of people survived and 32% of people died. And we had the simple bar plot for that in the end. So that was a numeric, that was our variable of interest. So hopefully some of you at least have some variable in your data set that is a nice outcome or response or dependent variable. These are all synonyms of each other. Outcome variable, response variable, dependent variable, it's all synonyms. But in this data set of ours, death makes absolute sense because it means I can take the other variables and I can compare it to the categories that I find in the death column. Everyone happy so far? Everyone is cool with that? Is anyone who wants to say that your data set, who wants to give me a hands up to show that, or tell us about your data set that has a natural sort of outcome variable in the data set you have? Does yours have one? Also, so you have one that has heart disease, no heart disease. Okay, so that's a very natural sort of response variable, outcome or dependent variable. Anyone else?
I do have one, but I don't have data pulled up, so I don't know which one exactly. But
So, okay, so reach out to either of us.
I think it's premenopause and like in menopause, premenopause. I think they're those two.
Okay, yeah, that's cool. What you can also do is maybe you have a numerical variable called age. And you can make some arbitrary, cutoff. You can say, look, I'm going to take everyone who's younger than, what would be, 65, and everyone who's older than 65. So just write a prompt to say, create a new column, use the age column. When it's greater than 65, put old. Okay, I'm sorry for the words, but if it's younger than 65 or younger, put young, whatever the two groups are. So you can take a numerical variable and change it into a categorical variable, which will naturally then divide your data set into a response variable with two categories. Is everyone happy with that idea? So look for one that creates something interesting in your data set for me. And then we had the summary statistics. We also calculated the interquartile range. And today we'll see why that might be important to us. If Python uses that describe method on that age column or the age series object, then of course, it's not going to do interquartile range for us. So I said, calculate the interquartile range of the age column using the stats module, because remember a week ago it did that longer code for me, but there's a IQR function in the stats module of SciPy, and you give it the series object, and then boom, let's just make it a little bit bigger as well, boom, out pops the interquartile range, which is just the third quartile 70 minus the first quartile 51, and that gives us the 19. But we said, let's group this by our outcome variable. So give me that summary statistic separately for those who survived and who died. And that's why I would maintain learning a little bit of code makes your prompt better. Because look what I did with this prompt. So when I rewrote this prompt, I said, calculate summary statistics of the age column grouped by, and that was a nice clue for the LLM to say, hey, but hang on, in pandas there's a group by method. And so, it used the group by method there. So just by knowing a little bit of code, picking it up as you see the LLM write some code for you, pick it up and see, well, hang on, every time it uses group by, let me use group by in my prompt. Okay, and your prompts will be better if you know a little bit of code. Cool? So we're just catching up on where we were. And then I did the same for the stats.iqr, and look at this code. It said df group by death, the age column, then dot apply to that, apply the IQR function. So that's kind of an interesting bit of code there and something for you to learn if you're just picking up Python along the way. And then we had our data visualization of that. I think you complained that those things were too wide. The boxes were too wide. I agree with you there. So that was our example of a numerical variable, and this was our example of a categorical variable. Once again, the unique values, all the same. And then this time, though, we wanted group by the death column. And so I didn't do the stacked one here. When I repeated it yesterday, I got separate ones, yes and no, died and survived, and then with anemia, no anemia. We can certainly see in those who died, the with and without anemia was almost equal, but in those who survived, percentage-wise or proportion-wise, those with anemia was a lot lower. Okay, so there might be something in it. Whether you have anemia or not anemia might have an influence on whether you die or not die. And that's what today is about. Can we bring some statistical analysis? And I'm not saying every one of you have got to do that, but if you want to polish your stuff today and next week, we're going to do some statistical analysis. So this is not a stats course, but I want to show you the common things that you could do with your own data set. And those are like the most common things you can do in data science if you're creating a report at work or anything like that. So I want to run through those basics. And I'm going to call that section, let's just change this one. So right there. So let me just see where we are at the moment. So we are at the, let's just go back up. So we're in the results section of our paper. So do remember that for each of these things, if I say unique yes or no there, then I want to see a markdown cell that says, this category had two values. This categorical variable had two categories, yes and no. Yes indicated people who died, and no indicated people who survived. So you've got to write that in an English sentence for me, because someone who's reading your data science project doesn't know maybe what that yes and no refers to. And yours might have 0 and 1 or some other encoding of what these categories are. So is everyone happy with that? Write an English sentence, explain to me who's going to read it, or whoever reads your project, what's going on inside there. What do those things mean? And when it comes to there, write a sentence then. This means that 96 died and 203 survived. Write that out, okay? So we're still in the results section. We've done our summary statistics and data visualization, which I called exploratory data analysis. And now we're going to get into the next section of results, and that is going to be our research questions. So you can see I've got 3 hashtags there. So it is a subsection still of results. Okay, so let me just go back there. Let's just collapse this so that we can see they all fit together under the results section. I'm just trying to keep things nice and neat. So this, 2 hashtags for results, 3 hashtags for exploratory data analysis, 4 hashtags for death. So I can collapse to the 4 hashtags, collapse to the 4 hashtags, collapse to the 4 hashtags. So they're all collapsed. Let's collapse to the 3 hashtags. And so under results, I've got exploratory data analysis. Next one's my research questions. So let's think about some research questions that we can come up with, and that's what today is going to be about. Can I come up in my data set with natural? And of course, that's not how it works in real life. In real life, you're going to have the research question first, and then you're going to collect some data, and you're going to provide a solution to your research questions. But we're just flipping it around at the moment. We've got our data set. We want to just take that data set, and we want to get some interesting information from that data set. We've already described it. And already from the data visualization and summary statistics, we noticed, hey, there's some differences between those who survived and those who didn't die. So those are going to be my natural research questions. And I chose these 2 because one is a numerical variable and one is a categorical variable. And can we remember our levels of measurement? By the way, if you look at today's notes, I'm not following today's notes. Today's notes that you have is like a little. So most of you probably have had statistics somewhere along the line at school or something. It's just a little refresher about distributions. And I want you to read that because there is some, I'll send the solution set. I didn't do it this morning. And then I will, so there's some questions. There's just a refresher on some basics of statistics. So you've got to read that and do the labs at the end. Cool? Okay, but we will remember that there are these levels of measurement. One is numerical. And that means I'm looking at every column in my data set and I'm deciding, that column, are you numerical or are you categorical? Okay, and under that, of course, remember we had ratio and we had interval. Ratio having a natural 0, a real 0 point, meaning the absence of what you're measuring. Interval, the 0 does not mean the absence, like temperature. We spoke about that. And this one's nominal if your categories do not have a natural order, and ordinal if it does have, like a Likert scale question. Okay, so you've got to decide those things, and I've chosen these 2 research questions so that we can have, in our discussion today, one example of numerical and one of categorical. So if I have a research question and it's about a numerical variable, what do I do? And if it's a categorical variable, what do I do? So I don't want to go deeper into these. We're not going to look at all kinds of modeling for the nominal and ordinal data. We'll do a little bit of modeling next week. But anyway, so there's my 2 natural research questions. There's a difference. My first one's about the difference in age between survivors and non-survivors. So that's a very natural question for my response variable, which has these 2 categories, survived and died, and I have a numerical variable. And so a natural question is there a difference in the age between those 2? And so how would I, what solution can I come up with that difference in age between survivors and non-survivors? So for those of you that have had a little bit of statistics, remember we have these statistical tests that we call hypothesis tests. Hypothesis tests. And a hypothesis is just, we can say it's a fancy word for a claim. We make a claim. A researcher makes a claim. So what would be a natural claim there for that numerical variable? What would be a natural claim? What can they claim?
Like
Say again? No, say again?
Like the null hypothesis would be 17. Oh, what's under the expert?
So this one at the moment, my research question is about, is there a difference in age between survivors and non-survivors? So now I've actually given you the solution. So a natural question would be,
is there a difference between the age and...
is there a difference in the age of those who survived and those who died? Now I want to give you a little bit of refresher on statistics. Remember, statistical tests like hypothesis tests, they are not about your data. So yeah, you were saying the right thing. So it's not about the data that you have. Hypothesis tests or statistical tests are about populations. Let me write that out very clearly. These claims are about populations. Okay, so I want to know the whole population of those who survived and died, not the ones in my data set, the whole population. And the reason why we do statistical tests is we don't have access to information about the whole population. So we take a sample from the population, a representative group of people from the population. That's what's in our data set. And we are going to calculate results here, but we use those results in inference. We infer that the results that we get from the data applies to the whole population. So it's always about a population. Okay, so what measure, and we've done these, the summary statistics, which one of my summary statistics will allow me to compare the age of the population of people who died and the population of people who survived? Which of my summary statistics can I use to compare the two populations to each other? Think about the summary statistics. What are they? Measures of central tendency. Mean, median, mode. Yeah, I saw the mouthing there. Mean, median, and mode. Okay. So which one of those would be a natural comparison between two populations as far as age is concerned, as far as the numerical variable is concerned? The mean. Okay, I can compare the mean age of these two populations. And we remember for categorical variable, the symbol that we use for mean, you don't have to remember these, just a little refresher, is the symbol mu, mu, mu. And so mu is the mean of the whole population, the mean age of the population who dies, and the mean age of the population who survives. But we have a little special notation. We change the notation if we calculate the mean from our data as opposed to the population. For those ones, we use x with a little bar on top. X being a representation of a random variable. Our random variable is age. And so I have, how many people did I have who survived? I've forgotten now. 203? Okay. So that gives me 203 random variables. The first person's age was x1. The second person's was x2. 3 was x3. Okay. I have 203 random variables, and I'm calculating the mean. So one comparison that I can make here when it comes to this numerical lot is to compare the mean, population mean of those who died and the population mean of those who survived. So think about the survived. So think about your data set now. You've got some outcome variable that has two categories in it. And you can think about those two categories. Maybe you made young and old, or maybe you had menopause, non-menopause, heart failure, not heart failure. So think about the age of those who die with menopause, without menopause, perimenopause or postmenopause, whatever. Those with heart disease, those without heart disease. It's the mean of this age that I'm trying to compare to each other. Okay, but I don't have access to these mu values, so what I'm going to compare here is these two. I'm going to compare the mean of everyone who died and the mean of everyone who survived. Survived. Is that a natural thing to do? That's all I can do. Okay, that would be a natural way to solve this problem. Is there a difference in these? And then she mentioned the null hypothesis. And so just a little reminder of that. Someone who makes a claim in the scientific method in real life with social media, anyone can make a claim, and if they're eminent enough or they get retweeted enough or whatever, then everyone just believes them. We live in a world where you don't need proof of anything. You just say whatever you want, and 50% of people just believe you anyway, and that's just horrible. In science, you cannot do that because you cannot just say, hey, here's a new drug, it'll cure your hypertension, just take it. No, you have to go through studies and preclinical trials and then clinical trials and all these kind of things to get the FDA to approve your new drug. Okay, so we cannot just make a claim and say, hey, that's it. That's snake oil, and the internet's full of snake oil. All the ads on YouTube or wherever the ad you watch will sell you something, and then they have their showed that it worked with their uncle, so that means it must work for everyone. That's just, don't get me started. Okay, so that's not what we can do. So in the scientific method, we say, if you make a claim, the onus of proof lies with you. You cannot say, prove me wrong. This is my claim and prove me wrong. No. You make the claim, you provide the proof. That's how the scientific method works. So if anyone, comes with that argument, prove me wrong. Yeah, I've told you the dragon story. I love the dragon story. Okay, so one of the best things you can do over the summer is read something about logical fallacies. Okay, it gives you an insight into the human mind, all this nonsense we come up with. Okay, logical fallacies. And there's lots of these, straw man arguments. You must have heard of some of them. And so that's that thing of, I've got a dragon in my house. Okay, that's the logical fallacy of the moving the goalposts, is what it's sometimes called. And people will have that argument. Sorry, I'm going to go in a tangent now. So I'm claiming I've got a dragon in my house. You say, nonsense, no one has a dragon. And I say, prove me wrong. And that's not how it works. I have to prove that I have the dragon. But, that's what the internet people do. Prove me wrong. Okay, let's go to your house and see the dragon. Okay, come to my house, you see it. There's no dragon. Oh, my dragon's invisible. Okay, moving goalpost. Okay, well, maybe we just put some sand on the floor. Okay, and the dragon's footprints, we'll see that. Move the goalpost. No, my dragon hovers in the air. Okay, maybe your dragon breathes fire and we can have an infrared, camera and we can see the fire. No, my dragon breathes room temperature fire, Moving the goalpost, that's a logical fallacy. So over the summer, buy yourself a book or get something about logical fallacies. They are fascinating things. Okay, we cannot do that. So our null hypothesis is we do not accept your claim. And a natural claim there would be, there's a difference in these two ages. That would be a claim. Researchers say there is a difference in the age between survivors and non-survivors. So that should be my proper research question. So I'm going to come down here. I'm going to create a markdown cell. And maybe I put a little star there. I'm going to use some LaTeX, and I'm going to say H sub 0, close. So that's a nice little H sub 0 there. There's no difference. Look at the nice large language model. Is this going to, solve all my problems? So it's written, and there is no difference in the age between survivors and non-survivors. So the null hypothesis is the standard, the baseline. We say, your claim is there is a difference. No. Until you prove so, we're going to assume there's no difference in the age between these two. And when I say difference in the age, one way to measure the age, not the only way, is to measure, as I said, these two sample means. But that's not, remember, what I'm interested in. I'm interested in these two, the population means, but I don't have access to all that data, so this is what we're going to work with. And so it says there, I'm quite happy with that null hypothesis. Let's try and write an alternative hypothesis, and look there, it gets written for me, H sub A. I like H sub 1, but that is notation in some textbook. There is a difference in the age between the survivors and non-survivors. Okay, so I want to see some research questions in your, you don't absolutely need it if you just have a bunch of summary statistics data visualization, because that's what your data set allows. You're still going to get a good mark at the end, a good grade, but this will be better. And so that's a very natural thing to do. So at least I want you to write those two things for me. And look at the markdown, very nice there, H sub 0, H sub A. I like H sub 1. The one thing that it didn't done for me there, it's not saying what in the population it's comparing. And supposedly I would want to say that there's a difference in the mean age between survivors and non-survivors. Okay, and the alternative hypothesis, there's a difference in the mean age between those. But we already know mean is not the only measure of central tendency for a numerical variable. We said the other one's median. So why don't I compare the two medians? And so that's the thing I want you to remember. It's not only that, there's no nice symbol for median, but let's write the median of those who died, and the median for those who survived. Okay, that would be another way to compare these two populations. Cool? So how do you know which one you should do? Well, we use in the hypothesis test a bunch of what we call parametric tests. Depends on distributions, and that's why I put distributions in today's notes, just to remind you a little bit of those, or give you something to read about it, to give you some background knowledge, is that we go for the mean, first of all. Okay, these parametric tests that we're going to do, they work on the mean. And we're going to see today sometimes that fails, and that's what today is really about. I want to show you what to do when that fails, so that we compare those two, the two medians. So that's what today is about, and that is, if you are going to do this, okay, maybe before you've done some project before and you've used a t-test, so I'm going towards a t-test here, but you don't just jump to a t-test. It might be inappropriate to compare those two depending on the data that you have. There are assumptions that you might fail, and then you'll have to compare these two. And in a standard statistical course, like who's had 2142 with me, we don't even do these. Not even in 6002 postgrad do we do these. But today, in data science, yes, we are going to do this because that is the proper thing to do, and that's what I want to show you today. And we're going to use AI to do that for us, so it's not going to be that much of a problem. Now, if we scroll back, and that's the nice thing, I've already done the summary statistics. I can see the difference in the means, and I can see the difference in the medians, and I can see the visualization of those. Let's go back to them and just have a quick squiz. Where's my summary statistics? There we go, EDA. And if we go to age, we've already done that. Look at this. It seems like those who survived were younger. Those who died, yes, was 65. Those who died was 59. If we look at the medians, 60 and 65. Okay, there seems to be a difference. And if I plot these two things, remember, this is not a plot about means. This is a plot about medians and interquartile ranges, because the black line in the middle is the median, remember? And we can see those medians are different from each other, and there does seem to be a difference between these two. But if there's enough of a difference to believe this claim that you've made that there's a difference between these two populations, is that enough of a difference? That's what the hypothesis test is. I cannot discern just from the numbers or from this plot that there's going to be a statistically significant difference between these two. And that's what I want to test. Everyone okay with that? Everyone with me? And so I have these two, and now we can say, well, I want enough evidence to either reject the null hypothesis and support the alternative hypothesis, or I don't have enough evidence to reject the null hypothesis. So for hypothesis test, please remember there are only two possible outcomes: fail to reject, just writing that on the board, fail to reject the null hypothesis or reject the null hypothesis and support or accept, depending on what words you want to use, and support the alternative hypothesis. You don't say you don't say I accept the null hypothesis, because if you take a course in statistics, we base everything on the null hypothesis being true anyway. We accept it to be true anyway, otherwise we cannot do any statistical tests. And we're not going to go into those things today. This is not a course in statistics. But those are my only two possible outcomes. I can either fail to reject the null hypothesis, then we're going to say, sorry for you making your claim. We stuck with the null hypothesis. There's no difference in the age. Cool? But if we do reject it, then we support the alternative hypothesis. We're going to say your claim about these ages being different in the two populations, okay? We're just inferring our results onto the population. We're going to say these ages are different in the population of people who died and survived in this setting. Okay, so is everyone happy with that? Now we've got to have some line in the sand by which we will decide between these two, and we're not going to go into those things today because, again, it's not a course on statistics. But the one thing that you can use a critical value approach, you can use a p-value approach, or you can use interval estimation. And we're not going to go into any of those. We're going to stick with the alpha value, and you've seen typical in public health, that's 0.05. And what that 0.05 means is that is your willingness to be wrong. You are going to create some distribution. That's what I want you to read the distribution notes on. And you're going to create this distribution. You're just going to say, I'm going to choose the 5% most extreme values. And if my result is one of those 5%, 0.055% most extreme values, I'm happy to reject the null hypothesis and accept. We say that's an error because you can only calculate possible outcomes given the null hypothesis is true. And we just decide amongst all of those possible outcomes, we're going to choose the 5% most extreme ones, and if my result is one of those 5% most extreme, I'm going to reject the null hypothesis. And what we express is a p-value. That's the probability of your result or more extreme. And we're going to say if p is less than alpha, if your probability of your result or more extreme is less than 5%, we reject the null hypothesis. But if this thing is bigger than alpha, we're going to fail to reject. We didn't find one of the 5% extreme values. We found one of the 95% least extreme values. Okay, and we'll see a visualization of that, so don't worry about it too much now. I'm just giving you a little bit of a background to what we're trying to do here to decide between these two. Okay, so now we've got to decide, and this is what you have to unfortunately remember, when you can just ask ChatGPT, it'll tell you, or Claude will tell you, what statistical test would be appropriate here? Who knows? You can remember from stats? What would be an appropriate statistical test here? T-test, great. Let's call it T-test. So the one that we're going to use here for these two is a T-test. Okay. And the other test we're going to see today, well, I won't say now, but we'll get there. Because this is the only two we're going to look at. Because it makes up so much of public health research. So in my other courses I spoke about a couple of weeks ago, I read a paper, and someone wrote a paper, they took the previous so many papers in the leading public health journals in the world, and they analyzed over the, was a year or 18 months, looked at all the papers that were published in these leading public health journals, and they looked at what were all the statistical tests used. What was at the top? Most commonly used. Second most common one, this one. Okay, so I'm not lying to you, it comes out of a paper. That's the most common test, and this one's the second most common test. So that's why I'm showing you today. If you can do these two in your data science project, you're doing what the majority of research papers have them, and then they've been published in high impact journals. Okay? So that's where we're going. We're going for a t-test. So remember, a t-test is a comparison of some numerical variable between two populations. I cannot do a t-test between three populations. That's another test. Okay, and if your data set is one that has more than two categories for your response variable, then reach out to either of the two of us, and then separately we'll help you with that. Okay, so a t-test is only for two populations. Clear? That's the limitation that we have there. And so that's what we want to do here, and I want to start doing this test. Now the problem with these tests are, and this is what we don't teach even in the statistical courses, because this is, this is more of an advanced topic, but I want you to know about this, is can I use the t-test? I've got to know, can I use the t-test? It gets even worse than that because there are more than one t-test, unfortunately. And the two that we're going to look at here is called students t-test and Welch's t-test. These have got different names. That one's called the equal variance t-test, unequal variance t-test. That one's called the pooled variance t-test. So that one's got 3 names at least, and this one's got 2 names at least. Okay, and that's what we want to know. So when you see, so write this down, I want you to know, when you have a numerical variable that you want to compare between two populations, you're going to either compare the means or the medians. Okay, we're going to go with the means first, and the test for that is the t-test, and 2 things you need to know. Which one do you use? And if it fails that you cannot use either of them, then we're going to compare these two. So that's got to be your little sequence. Write it down. You've got to have a little flow chart for this. Okay? So that's exactly what I want to do now. Now, some of the assumptions are just easy assumptions. Okay? I have 2 populations. That must be in the assumptions. Otherwise, I cannot use the t-test. It must be that I have a numerical variable for these 2 populations. The same numerical variable. I cannot compare age to blood pressure. Okay, that's a different thing. That's correlation or linear regression. And we'll get to that next week. So this is what I have. Okay, I first want these assumptions. I have 2 populations. I have the same numerical variable. One thing that we always have to assume, okay, that every person in my study is independent from every other person. I haven't got Johnny 5 times in my data set. Okay, I cannot have that. Technically, another thing that I cannot have is Johnny and his identical twin, Freddie. Okay, they can also not be because they're not independent people. They've got the same genetic, genotype, so technically they are the same person. And I use different study design for homozygotic twins are special cases. There's another t-test for that. That's called the dependent sample t-test. We won't do that one today. Okay. Another reason to use a dependent sample t-test is if you have something that you measure before. You measure blood pressure, you give them an intervention, and you measure the blood pressure again. Now, every one of the 2 populations actually comes from the same person. I've measured their blood pressure twice, and that makes them dependent. It's not 2 separate populations. And then I would also do a dependent sample t-test, but we're not doing that today. So I'm going to assume those simple things. These are all independent people. I've got the 2 populations. I've got a numerical variable, so let's not talk about those. That's, I'm going to assume that to be obvious. But the one thing that we need to do is to know this thing, and you also got to write this down. For me to compare the two means, there's a very important assumption that has to be met. That assumption is the following, that this variable age is normally distributed, you know the normal distribution, bell-shaped curve, in the population from which your data comes. So I need to know, in those who survived and those who died in those two populations, is age normally distributed? Write this down. That's the first thing that we are going to check. Is the age normally distributed in the population of people who died and in the population of people who survived? And this I absolutely want to see in your data set. So the first test that we're going to do is the following. So let's write something in a markdown cell. I'll share this with you, but anyway, we're going to do let's call it, there's a couple of you can choose from, but the one I'm going to choose today, a Shapiro-Wilk test. Do a Shapiro-Wilk test, look at what it wrote for me. Do a Shapiro-Wilk test to check for normality of the age distribution in both groups. I like that. I'm just going to take away all of this. We don't need this for now. Okay, write that down, because once you do this, I've got a numerical variable, I've got two populations, I've got my null and alternative hypothesis, what I'm stuck with and what your claim is, and the first thing we're going to do is check for normality. That's not normality in your data, is this thing normally distributed in the population from which you came? And the problem is, I don't have access to the whole population, do I? I only have access to these 203 people who died and 69 who survived, or whatever, how many survived, the other way around, I cannot remember. That's all I have access to. And so this test, there's some others as well, they are meant to help you to decide if this variable is normally distributed in the population. Okay, that's all you have to know. Again, it's not a statistical thing. So let's write a prompt to try and do that for us. I'm going to say, conduct a Shapiro-Wilk test on the ages of people who survived. Okay, I don't know why it's putting that. That's all I want to do. Survivors equals, and look what it's going to do. And that's completely wrong. It's making a huge mistake there. Because if we go back, that's why we have it. When we did the verification of our data, it didn't have 0 and 1 in it. It had survived and died in it. So let's go back there, because now, unfortunately, some other time you'll have to help out this LLM. Look at the death. It didn't have 0 and 1 in it. It had no and yes in it. Do you see that? So the code that it wrote here was completely wrong. So I'm going to help it out now. Shapiro-Wilk test on the age column, selecting only no from the death column. Okay, I'm helping it out here. And that's what it's done. Look at that. Stats.Shapiro, df death equals no age. Okay, that looks brilliant to me. I'm going to run that test, and there we go. You see that? So you really have to write the prompt. And a prompt is good if you know your data, you know a little bit of some coding practices, okay, and you know a little bit about stats. And that's the only thing in stats is the stuff I'm going to tell you about this week and next week. So conduct a Shapiro-Wilk test on the age column, selecting only no from the death column. That really helped the AI out, because now it's done that stats.Shapiro, so I can see Shapiro is a function in the stats module. It's selecting the death column and only those that had no in the death column. And then it selects the age column, and so that's what I'm going to get. And you get two things here. The result, the first one is your test statistic. We don't have to care about that. The only one we're going to care about is this p-value. And remember, our cutoff here was 0.05. And look at the value we found there, 0.004. That's definitely smaller than 0.05. And I said if it's smaller, we reject the null hypothesis. Okay, but now I haven't told you what the hypothesis for the Shapiro-Wilk test is. And it's quite simple, that you're making the claim that this is not normally distributed in the population. Null hypothesis, it is normally distributed in the population. So it just makes natural sense. So here, it's such a small value, 0.004, 0.05, much smaller than 0.05. So I'm going to reject this null hypothesis that this is normally distributed in the population. And so I'll have to accept that age is not normally distributed in the population. So let me write that down here. According to the Shapiro-Wilk test, age is not normally distributed in the population of survivors. Okay, so I want to see your statistical test, and I want to see that you understand what it means. Get the LLM to help you out with that. Okay, now I've already run into a major roadblock. It means I cannot use a t-test. I've already failed on the first hurdle. Okay, but because this is a tutorial, I'm just going to soldier on and show you what would I do if this was a big number, 0.65 or 0.06, anything larger than 0.05. I would have said age is normally distributed in the population. Okay, so I'm going to soldier on because I want to show you all the stuff. So my next is going to be conduct a Shapiro-Wilk test. Conduct a Shapiro-Wilk test to check for normality of the age distribution. No, that's not what I want. So I'm going to continue with my little previous prompt, Shapiro-Wilk test on the age column selecting only yes. What did I do? Yes from the death column. So I'm helping my model out. And look at that. I love that code. Stats.Shapiro, death equals yes. Yeah, that looks right to me. I'm going to run that one. And there I see a value of 0.02. So there I also reject the null hypothesis. Age is not normally distributed in the population of those who died. Okay, so I'm going to copy and paste this one because I just don't want to retype everything. Copy, and I'm going to come down, create a markdown cell. I'm going to paste that, but I'm just going to change that to in the population of non-survivors. Okay, so I failed again. If you fail one of those, you should not. Now, sometimes we say that the t-test is robust against some violations, okay? But now it becomes a human decision. When is a violation enough or not enough? That's your decision as a researcher. There's no black and white here. Okay. So I'm just going to soldier on. I'm going to assume that, hey, I haven't failed these two hurdles. I'm still trying to do a t-test because it is my priority to do a parametric test versus a non-parametric test. It's always my aim because this test is better at finding differences than this test. Okay. As I'm pointing at, these parametric tests are better at testing your hypothesis than, being very generic here, than non-parametric tests. Okay, doing the median. So I'm just going to soldier on because I'm going to assume most of you are going to get there large p-values. So you're not going to reject the null hypothesis. So, no bird, no. So that's your first thing. You have to check for normality. Write that down. Check for normality. The second thing, but you cannot just do it for the whole age group. You've got to do it separately for the two groups, two populations. Okay? That's the first hurdle. The second hurdle is which one of these two should I use? And so write this down. The test for that is the Levine's test. Okay? So I'm going to do my next thing. I'm going to say code, use Levine's test to, and let's see what it wrote. To check for homogeneity. Now homogeneity, that's a fancy word for compare the two variances. Remember standard deviation and variance? I want to compare the two variances. If the variances of age for those who died and survived are very close to each other, I can use the equal variance t-test, otherwise known as student's t-test, otherwise known as the pooled variance t-test. If these two variances of the two age, the two groups, the age is very different from each other, I will have to use the unequal variance t-test, otherwise known as Welch's t-test. And there's no S there in Welch. Okay. Right. So I like that. Use Levene's test to check for homogeneity of variance or equality of variances in the age column between the two categories of the death column. I like that one. I'm going to accept that. Stats.Levene, and now it's going to create these two groups for me, those who survived and those who died, and every time it's the two ages. Now again, Levene's test is the null hypothesis is these two variances are equal to each other. Alternative hypothesis, they are not equal to each other, just like superior work. It is normal. No, it's not normal. It is equal to variance. It's not equal to variance. Okay, that's the null and alternative hypothesis for these two. So let's run that, see that that worked out. And look at my p-value. It's tiny at 0.07. Okay, so I can write my little markdown there according to Levene's test. And it's written the rest for me. There is homogeneity of variances in the age distribution between survivors and non-survivors. Okay, and there is, I'm going to write that just in more simple terms, there is inequality. There is inequality of variance in the age distribution, just to make it, easier to understand. Okay, so if you have that case, you'll have to use Welch's t-test, and if your p-value was larger than 0.05, failed to reject, you'll use student's t-test. So those are the steps I want to see. I want to see a step for normality, and I want to see a step for, homogeneity of variance or equality of variance. Okay. Now I'm doing it here for the sake of argument, so I can show you everything. But what I want you to do in real life is as soon as you have hit the wall and any one of these p-values are less than 0.05, stop. Don't carry on and do all these things that I have done. Okay, so everyone happy? Everyone with me on that one? Okay, I'm just showing you all the steps. But I've already faltered at the first hurdle. I can no longer do a t-test. If I'm strict about my decisions, I can no longer use a t-test. So I need not have done the normality in the other group, and I need not have done Levene's test because I've already failed. I can no longer do a t-test to compare the two means. I will now have to use a non-parametric test to compare the two medians to each other. Everyone happy with that? But I'm just soldiering on to show you how to do that. Okay, so I'm also just going to show you both of these tests, how I would do student's t-test and Welch's t-test. So let's have a look at those. Okay, so I'm happy with that. But let's soldier on. The large language model is going to go nuts because I'm breaking all the rules here. I've already failed, but I'm soldiering on. So I hoping that it helps. Okay, so let's do that. I'm going to say, do the following. Conduct an equal variance t-test to compare the mean age between survivors and non-survivors. I like that one. Let's see what it's done for me. And look at this little argument here. Equal underscore var equals true. That's the function that determines that I'm doing student's t-test, the equal variance t-test. And so let's run that one. And let's look at the result. Let's look at our p-value. Look at that thing, times 10 to the power negative 6. That's 0.000008916. So that's scientific notation, 8.91 to the power, times 10 to the power 6, negative 6. Okay, that's that's much, much, much smaller than 0.05. Okay, so what would the result be? I can now write my final conclusion. Okay, I'm just going to leave the conclusion for now. I'll just tell you what it is. I would write something like, there is enough evidence in the data at the 5% level of significance. We teach this in 2142, 6002. There is enough evidence in the data at the 5% level of significance. We chose that to be our line in the sand. We made every decision based on whether this is less than or more than 0.05. Okay, that's the most common one to choose, but you can be stricter. Maybe you want to use 0.01. Okay, that's your type 1 error rate. You know whatever decision you come to, there is a 5% probability that you are doing the wrong thing. If you reject the null hypothesis, there's a 5% probability that you did the wrong thing because you are rejecting something that's completely possible under the null. And that's something for a stats course, not for now. But we'll choose that as our cutoff. So I'm going to say there is enough evidence in the data at the 5% level of significance to support the claim that there's a difference in the age between the population and of people who survived and who died. Use the word population in your conclusion, because we're making inference about a population based on sample data. Okay, I'm going to write that sentence a little bit later, but I'm not ready yet. I just want to show you the unequal variance t-test. So imagine I would have to use an unequal variance t-test because when we did the Wien's test, we showed that there is inequality in variance. Okay? So now I'm just going to do the other one for you. Okay, conduct what did I say? An unequal variance t-test between those two. Okay, and then you just see what it did there. Equal underscore var equals false. It's the only difference between those two sets of codes. And you'll see we're going to basically come to, where's my p-value? The same sort of here. This was 4.7 times 10 to the negative 5. See that result difference in the p-value between those two tests? There's a difference. Okay, but it's much less than 0.05 anyway, so we're going to come to the same conclusion. Okay? But I hope now that you know the steps that you are to follow. Now, I should not have done either of these two because I already stumbled at the first hurdle. Okay, I'm just showing you what you would have done if all these assumptions were met. For the both Shapiro-Wilk test, you got much bigger than 0.05 or anything bigger than 0.05 or 0.05 and bigger, to be technical about it. And then your Levine's test should also have had a p-value of more than 0.05. Then I can use either the equal or the unequal variance t-test depending on what my Levine's test made me decide to do. Okay, but we already failed at the first hurdle, so now I can no longer do a t-test comparing the means, actually these two things in the population. I now have to compare the medians between the two. Okay, and that's a non-parametric test. It does not depend on a distribution like what I have in the notes for you this week. It does say we're not going to use that. We are going to use a different statistical method. Does not depend on distributions. And the problem with distributions is distributions depend on all these things that we had to test, the assumptions. Those are assumptions for the use of a parametric test depending on distributions. These non-parametric tests says, no, we don't care about those things. We already failed those assumptions anyway, so we're going to do these. And that test is called the Mann-Whitney-U test. Okay, so my non-parametric things here is the Mann-Whitney-U test. Mann-Whitney-U test. It's got various names. That's not its only name because there were so many people involved in this. Okay, it's got a bunch of other names as well. But let's use the name Mann-Whitney-U. And that's the one I would have had to choose. Okay, so let's go for that one. I'm going to do code. I'm going to say conduct a Mann-Whitney-U test. Mann-Whitney, okay, let's get the spelling right. Mann-Whitney-U test, okay? And the code was written for me. Look at that, stats.mann-whitney-u. Okay, is that the right thing in stats module? Let's see if the code executes. Hey, it brilliantly does. Look at that. Okay, and then I have the results of the Mann-Whitney-U test. That's the test statistic there. There's our p-value, sorry. 0.001. Okay, same thing. I'm still going to use 5% as my line in the sand. And look at that. That's less than 0.05. Okay. Now I just want to go back to why I didn't change anything here. Look at my null and alternative hypothesis. It says there is a difference in the age between survivors and non-survivors. I'm going to change it slightly and say between the population of survivors and non-survivors. And this one I'm going to change the age between the populations of, okay. But look at that. In a typical stats course, we're only going to deal with these parametric tests, and I would have written there's no difference in the mean age between populations of survivors, and there is a difference in the mean age, but I didn't put mean in there. That's a safer thing to do because it's not to say that I am going to be able to do a parametric test to compare these two to each other. I have failed that assumption, so I've got to use a non-parametric test. So it's good for me not to put mean or median in there. That leaves it open for me to do the kind of comparison that I want to do. Happy? And now I can just delete all these nonsense things that I did because I should never have done them. But now I've got my result there. It is less than 0.05. So let's write that test conclusion now. So I'm going to say there is enough evidence in the data at the, and I'm going to write 5% in LaTeX. Oh, and that's, oops, that should be percent. And that's how I would do it. Because I'm putting my percent symbol inside of LaTeX, I've got to do the escape character before the percent. So percent. There's enough evidence in the data at the 5%. Let's carry on. Level of significance. This is what I call this, my level of significance. At the 5% level of significance, to show that there is a difference in the, but now I cannot say mean because I failed the assumption for the comparison of means. I'm going to now say in the median age between the population of survivors and non-survivors. And I cannot leave it there. If I failed to reject the null hypothesis, if I got these big p-values, I could stop right there. Because now I'm still stuck with the null hypothesis, and the null hypothesis said that these two things are equal to each other. And so I would just stop there. Maybe the means were 61 and 62. They were too close to each other. So I don't say anything about my results. But now I have rejected this null hypothesis. I am now supporting the claim that there is a difference in the median. So remember to put mean here. If you didn't fail those assumptions and you did use a t-test, then just change this. Of course, you'll never do the Mann-Whitney-U because you were allowed to use that. Between survivors and non-survivors. But because I've rejected this, I now have to say something about the claim because we are now going to trust your claim. And so I'm going to say something like, in fact, the median age of non-survivors, and what were my two medians? Can you remember? Was 60 and 65, was it? Okay, yes, thank you. In fact, the median age of non-survivors is 5 years more than median age of non-survivors then is 5, no, that was the survivors. The median age of survivors is 5 years more than non-survivors. Okay, so that's crucial for me to see in your data science project, that you can interpret these results. And look how easy it is. We don't have to have a whole course in statistics to be able to do this. Okay, we have to understand some basic things. If I have a numerical variable and I want to compare between two populations, assuming that they're all independent people, okay, I can test, my main thing that I want to do is compare the two means in the population. For that, I'm going to use a t-test. But first, I've got to check, can I use a t-test? So I'm going to check for normality. Okay, Shapiro-Wilk test for both of those. If both of those have got large p-values, then I can decide which one of these two can I use. Okay, and because, you know, the Levine's test, if the p-value is big, I can use that one. If it's small, I must use this one. Equal variance, unequal variance. If I failed any of those normality assumptions, I've got to immediately, you know, drop my attempt at doing a parametric test, and now I've got to do a non-parametric test whereby I compare the medians, and that is going to be the Mann-Whitney-U test. Okay, I will put this up, you know, convert this in the end to a HTML file, and I will put this on Blackboard so that you can have, you know, some notes, because I'm not sure everyone's making notes about these steps that you have to follow. Okay, so these things we don't typically teach in the introduction to statistics, both undergraduate and postgraduate. But I think this is very important for us here, and look how easy it is if we use technology. we can have a full understanding of what we have to do in statistics, okay, by just following these simple rules. Okay, so that is it for comparing a numerical variable between two populations. If you have more than two populations, then you cannot do a t-test. What are we going to use then? Who can remember?
Is it chi-square?
No,
I was going to say chi-square.
no.
ANOVA?
ANOVA, analysis of variance. Okay. And if you take my courses in stats, you'll learn analysis of variance is nothing other than linear regression with categorical variables. Okay, so, but we use analysis of variance. Okay, and so if your data set has more than two, just reach out to me. Okay, and I'll just show you then, but you can also do it right there. You'll still have to go through the normality check. So you'll have to check that these things are normally distributed in the population. Okay, and then instead of saying do a t-test for me, you'll say do ANOVA. Just by the way, if you fail normality, what is the non-parametric version comparing these things? That's called the Kruskal-Wallis. Let me write it down. Okay, so if you have more than two, you're going to do Kruskal-Wallis. Okay, Kruskal-Wallis test would be the non-parametric version. So t-test, Mann-Whitney-U, ANOVA, Kruskal-Wallis. Okay, so we're done with numerical variables, right? Now we're going to move on to what would I have to do if I want to compare two categorical variables to each other. Okay, so I had a numerical variable between two populations, the populations of survivors and those who died. But what if I want to compare a categorical variable between those who died and who survived? Okay, so that's my next question there. And you can see the term that we use there. This is a comparison of a numerical variable between two populations. But what about the comparison of a categorical variable between two populations? And two populations is naturally a categorical variable. Survived and died is a nominal categorical variable. Okay, so I want to keep that idea that my two populations is still determined by a categorical variable, but now I want to compare another categorical variable to this categorical variable. And the term that we use there is called association. The association between two categorical variables. And clearly people with anemia, and anemia yes, anemia no, that's categorical. And death, yes and no, is also categorical. So I'm comparing a categorical variable between two populations. Okay, and that is determined, that's called association. Okay, what would be a natural null hypothesis testing the association between two variables? What would then be a natural, if I use the term association? Under null hypothesis, or what would the claim be? So let's use this example of people have anemia and they don't have anemia, and they died or survived. What would be a nice claim to make? What would be a natural claim to make?
There's an association between the presence of anemia and non-anemia.
And outcome. Yeah, those two things are associated with each other. So whether you have anemia or not determines whether you will die or survive. It has an impact on whether you died or survived. That's a natural claim to be making. Okay, so our research question about the association would be, let's write those two things. Someone's claim and someone's, I'm going to plonk it right there. Come on. Now you can see I've already done something. I'll get to that a little bit later. So let's make a null hypothesis, H sub 0. There is, okay, and now the LLM is not helping me out, can I say? There is no association between anemia and death. Okay, my claim that someone is making is there is an association between anemia and death. So whether you have anemia or not is going to have an impact on whether you survived or died. The other term that we use is independence. Okay, under null hypothesis, these two are independent from each other. The claim is that they are dependent on each other. But association is a nice word, a nice term, and so we're going to use that there's no association between them, but you claim that there is an association. That's a natural null and alternative hypothesis. Is that okay? Okay, now I want you to think about the following for categorical variable. What does your spreadsheet look like? Clearly there's going to be an anemia column, and the data set that we have has got the British spelling, we spoke about that, and it's going to have a death column. Okay, in the anemia column, this person didn't have, this person had, this person didn't have, this person didn't have, this person had. And in the death column was maybe they died, yes, they died, yes, they died, no, they died, no, they died, yes. Okay, something like that. Okay, how many unique combinations can I have? If I look at every person, 4, yes. Okay, yes, 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 no, no, yes, no, no. That's the only 4 I can have. So what would be a nice, and we've done it already, what would be a nice summary statistic for that? A contingency table. Okay, so I want a table that has, here we have, do you have anemia? Yes, no. And that you died, yes, no. So I can just count those 4, and that's why I said there are 4 possible values. 4 possible values. And so what we want is a contingency table. And if we go back here, well, I did it down here earlier just to show, there's my contingency table. They've got anemia, no anemia, death and no death, 46, 83, 50, 120. Okay, I've already done that for you. And the way that I did that was here, create a contingency table. I was just playing with it yesterday. Create a contingency table of the anemia and death columns and assign it to the variable contingency table. So it created this contingency table equals pd.crosstab. So the crosstab there is a function, not a method. We're using it as a function instead of using it as a method. So it's pd for pandas.crosstab. The one that you list first is going to be the ones along the rows. And the one you mentioned second, like I mentioned death second, goes along the columns. So just make yourself, in your own data set, that favor. When you write your prompt, write the one that you want along the rows. So that's the one that is going to be, well, whether you had anemia or not is going to determine whether you die or not. Okay, so do it in that order because it just makes natural sense. And this table, unfortunately, then comes up in the wrong way. And it's doing it alphabetically because N comes before Y. Okay, but when you do this by yourself, it is better to put the thing that you're interested in, yes, you have anemia, and yes, you are dying, put those first, and then the other one second. Okay, because that table turns out the right way so that you can do other measures of association. And I'm not going to do that here, but if you are interested, just reach out. That is risk difference, relative risk or risk ratio, and odds ratio. Those are 3 levels of measurement we can do for 2 binary categorical variables. So I've only got 2 possible outcomes and 2 possible outcomes, then I can do those. But now I'm not going to do those measures of association. I'm going to do a statistical test, a hypothesis test. And now the 2 of you said, what did the 2 of you say? What test? Chi-square test. That's the one here. So t-test and Mann-Whitney-U. And for 2 categorical variables, it's a chi-square test. And it's chi-chi with a hard K, chi, and it's this funny Greek letter, looks like an X, squared, the chi-square test. Okay. Right, so that's the one that I want, the chi-square test. So I've got my contingency table, and the table that it produced is that. But it just tells me that 120 people didn't have anemia and they survived. 50 people didn't have anemia and they died. 83 people had anemia and they survived. And 46 had anemia and they died. And we did that before in our summary statistics. We've already done it. And we saw those bar plots. And there seemed to be something in it. Because remember, those who died was an equal number almost of people survived and died with anemia and without anemia. But on the other hand, there was a big difference between the 2, anemia and no anemia. Okay, so there might be something in it. Look at these 2 ratios. It's 50 to 120 and 46 to 83. 50 and 50 is 100. 46 and 46 is 92. Okay, so there seems to be a little bit of difference. Is that enough of a difference in proportions? Okay. 50 to 120 versus 48 to 83. Is there enough of a difference in those 2 proportions? That's what a chi-square test is going to do for me. So null hypothesis, there's no association. Alternative hypothesis, there is an association. All I need to do this test is I need this contingency table. And now I can do the chi-square test. Now the chi-square test has many names. It's Pearson's chi-square test. And Pearson wasn't a good person. You can go read on his history. I like to say that. He wasn't a good guy. But he did a lot in statistics, so there we go. Even this guy, so the people who've had stats will know that I've mentioned this in that courses. What is this guy's real name? His real name wasn't Student. His real name was William Gossett. He worked in 1905, time of Einstein, with the Guinness Brewing Company, and they wouldn't allow him to publish. But he really, he's really wanted to be academic, and so he published under the pseudonym Student. Okay, he did study under Pearson, and we have him to thank for all these wonderful things we have. But I think, as the story goes, Pearson wasn't very impressed with what he said. But now, it's very impressive to us what he did. Okay. So it's Pearson's chi-squared test, otherwise known as the chi-squared test for independence, otherwise known as the chi-squared test for association. All the same, different names, same thing. Okay, and that's all we need is that contingency table. I've just rewrote it there with my little markdown, so it's a nice little table. Okay, so let's do that, and we're going to say conduct a chi-squared test for association between anemia and, I've got to do the British spelling, anemia, British spelling, and death, using the contingency table. I'm just going to add to my little prompt, because I want a couple of things back. Remember here we had to check some assumptions? Here we also have to check some assumptions. So we better do that. And the way that I want you to remember is return the test statistic, p-value, and the table of expected values. Okay, and it's done for me all of those. And it looks like it's going to print out all of them for me as well. Okay, I've just got to check the order there. And it took the stats module. It had a chi2 _ contingency function. And as argument, it sent through my contingency table. And it returned 4 things, actually. It returned the chi-square statistic. Now, in stats, I call that x squared. The x squared statistic follows a chi-square distribution on some degrees of freedom under the null hypothesis. Don't worry about that. What I have back there is my test statistic, which is 1.02. My p-value is 0.307. Am I going to fail? Am I going to reject the null hypothesis? No. My p-value there it is bigger than 0.05. Failed to reject the null hypothesis. Remember there, failed to reject when p is larger than alpha. Okay, so I don't have enough evidence for this claim of yours. Okay, we're going to fail to. Now, the final thing that you see here is an expected table. If the null hypothesis were true, and how many people did we have in our study? Say maybe 300, I cannot remember the number. Okay, what you do is, if you have so many people, and these two variables are independent from each other, what numbers would you expect in your table? If the null hypothesis were true, now there's a way to calculate that. Take the stats course and I'll teach you how to do that. But look at those numbers. If the null were true, I would expect. Now, unfortunately, the way we calculated, and it has to be that way, there's going to be decimal places. And you don't have a fraction of a human being, but that's what we have in the table. 115.4186 people, 54.58 people, 87 people, and 41 people. And what the chi-squared test does, it tests or calculates a test statistic called the x-squared statistic there that measures the difference between what you observe and what you would have expected. So the difference between what we observed on our table there, the 46, 83, 50, and 120, what I would expect is, if I look at the top table, because it's going to do the same order as this order. So I saw there, I got 120, but I expected 115 under the null. I got 50, but I expected 54. I observed 83, but I expected 87. I observed 46, but I expected 41. So why would I need to know that? And here's the assumption for this test. First of all, the obvious stuff, I've got to have 2 categorical variables. They don't just have to have 2. So if you have a categorical variable that has many outcomes there and many here, you can still do Pearson's chi-squared test. Okay, that's the beauty of the test. But what you want, the assumption that you want, so also they all have to be independent from each other, like always. okay, we're just going to assume those things are true, is that all of those expected values must be at least 5. And if you have many and many, so your table's got a lot more numbers in it, we'd say at least 80% of them have got to be at least 5 or more, in the expected table, not in the observed table, but in your expected table. That's why I want to see the expected table there. That is how I test the assumption for the use of this test. And look at them, 115, 54, 87, 41, they're all bigger than 5. Some textbooks say 10, but we normally take 5. And so that means I can use Pearson's chi-squared test. Okay. If those numbers were all small, I would have to use another test. That's called a direct test in this case, and that would be something like the Fisher's exact test. Okay, that would be my alternative. There's always some alternative, okay? And so this is what we have, and now I can write my conclusion. I've checked there, they're all bigger than 5. I'm happy. I don't have to do anything else, and all I have to do now is write my conclusion. So let's write together. There is not enough evidence in the data at the 5% level of significance to show that there is an association between anemia and death. Boom. I stop there. I don't have to say anything about my results because I'm done. Oops. Let's fix our little error there. 5% level of significance. Done? And then I'll just tell you a little bit about that. If you did find a significant difference, you can do these measures of association. Risk difference, relative risk or odds ratio. I'm just going to say it. You can forget it. Remember your study design. If you have a case control series, you cannot use risk difference and you cannot use relative risk or risk ratio. Then you can only use odds ratio. If your study design is an experimental study design or you have a cohort or cross-sectional study, then you can use all 3 measures of association. And you would have to express those when you did reject the null hypothesis. But that would be only if you had 2 and 2. But if you had 3 and 3 or 3 and 4 or whatever the case might be, then you cannot do those measures of association. Then you will have to use a regression model. And typically they will use logistic regression, okay, or some other generalized linear model, and that will give you all your coefficients, beta sub 0, beta sub 1, beta sub 2, and we would express those, but that's not for now. Okay, I'm just going to assume that you have this set up. Okay, next week I'll show you a little bit about logistic regression, linear regression and logistic regression. So for those of you really sophisticated and you want to include a little model, maybe not for this project, but that you have some background in doing that, and doing it that easy as we're doing this, just with using the AI to do it. I'll show you that next week. Okay. But is there any questions, comments, or concerns about this? Those 2 things, comparing a numerical variable between 2 populations, categorical variable between 2 populations. Will you be able to do it yourself now? Okay. If I post this so that you have something to work from. Okay, so you're going to remember the steps that you have to go through. And this is a data science project. You need to show people that you checked for these things. Usually in a paper that you publish, you'll say, in the method sections, we tested for, we use both parametric and non-parametric tests. This is what we do to decide between the 2. And then people know down the line, they suddenly see Shapiro, they suddenly see Mann-Whitney-U test, they suddenly see Kruskal-Wallis, they suddenly see these things. They know that you did these things. They know that you checked for these. But now I challenge you to go read papers, and there are studies on this as well. How many people don't include that in the method section? Which means immediately you can take that paper and you can basically throw it in the rubbish bin because you don't know whether they did the right thing. Did they check for these things? Okay, and a proper data scientist will check for these things. And that's why I want to see it in your work. Did you check for these assumptions? Did you check that you are using the correct statistical method, the correct statistical test? That is unimaginably important. Otherwise, you are going to publish rubbish. Your results will be fine, but I can't trust them. I don't know if you did the right thing or not. So in your data science project from now and forever, you will include these things, even if your professor can't remember those things and forget that those should be in there. From now on, you will do this because that is the right way to do things. Okay, if you're very interested, my particular interest lies in neither of these things. Okay, parametric and non-parametric tests. I like simulations. Okay, and there are two kinds of simulations that I basically like to do. Monte Carlo simulation, and that comes from Monte Carlo casinos. Okay, because you can simulate through random events, randomness, a result, and the bootstrap method for confidence intervals. And why I like those two things, they don't depend on any of these assumptions that we have to make. Those simulation methods use only your data and randomly select from your data to produce results. And I love that because we are always making assumptions. Think about this as my final word to you today. I'm just going to I'm just going to do the attendance, don't go. Sorry, you still had your hand up. Don't let me forget, okay? Think about this thing now. And all these tests, all the statistical tests that you do, you are interested in the population. You don't have access to all the data in the population, and hence we have statistics because we're going to infer results from sample data onto that population. Okay. But what do I have to know that I'm not 100% sure of in many many research projects? Did you choose these people so that they are representative of the population? Maybe you introduced bias when you selected these people, and bias is everywhere. There is so much bias in data. Okay, and we just assume that everyone did a good enough job to select randomly from the population so that these people that you have in your study are representative of the population. But maybe, you woke up on a bad day and you introduced some bias in the selection. Maybe you recruited your people on a Tuesday and there's something special on a Tuesday because only certain people go to, the community healthcare center on a Tuesday. Maybe that's the old age home day. And you've introduced massive bias in your data. There's racial bias, age bias, all sorts of bias gets built into the data that you have. And now, this lot, I'm inferring the results that I get here onto the population, because why do I do that? Because you do your study here in DC, but someone in Chicago reads your paper and they want to know, can I apply what you found to my population in Chicago? So we've got to assume that your results can be inferred to a bigger population. That's why it's so important to us. Can you see that? Okay. But now you introduce bias here, and I just want to say that this method of Monte Carlo method and the bootstrap, okay, they use only this data, and they don't say, so and what the results of that say is that your results are only applicable to a population that looks exactly like this. So if this has bias in it, I don't care, because my results through those two techniques, which I haven't shown here, is only applicable to populations that look like this. And I sidestep all this nonsense of assumptions and, bias in your selection, and that is in every research paper. And so many people have written papers about how much of the published research is wrong. And depending on the paper and the method that they use, most people would have as a lower limit, 80% of all research papers are wrong. And we use it all the time. And there's good evidence to show that most of research papers are wrong, okay? And so my particular interest is, I sidestep all of that and I use only the data, but I also know that, it's only applicable to populations that look like this data, as opposed to you doing all your fancy things and you're saying, well, I've passed, I've done all these assumptions, it looks like I can infer to the greater population. No, I don't like this thing. And why am I so strict about it, why other people might not be? Because, in my setting of clinical medicine, you're actually standing there in front of a person making decisions. Okay, you want to do the kind of best thing. So if 80% of what I think I know from research papers is wrong, I'm kind of scared. Okay, so I like to be much more stringent, and I like the simulation idea. But that's certainly not the norm. Okay, there's lots of statisticians, and they work out all sorts of wonderful tests. But I tell you, I'm always nervous when I say to you, look, we've done this test, this and this, we're going to do that and that. That's a huge impact. I want to be sure that I'm doing the right thing. And I can tell you now as a clinician, I'm not always sure about that. The data leads you astray. Statistical tests can lead you astray. And so I'm very careful when I read a paper. Okay, it's got to tick many boxes before I believe that. Or, we wait for big societies to say, look, the Society of Thyroid Surgeons of America, they will bring out these statements and say, this thyroid disease will treat this way, because that's what the best evidence shows now. Okay, then I'll go with it. Okay, but there are cases where you can put those papers together and you say, no, you know. So it takes a lot of new evidence to shift what we're saying is the standard of care right now. And I'm just trying to paint a little picture of when we do all these fancy things, you still have to take everything with a grain of salt. Okay, but that's just a philosophical thing that I want you to think about, the stringency of, you know, the fields in which you're working. Think about it carefully. Okay, but for us today in this data science project, I want us at least to be careful about our analyses, and we will go through these steps. And as I say, they are well beyond what we teach in the basic introductory statistical courses. So you've already seen a lot more than that. And that's what I want to see in your projects. Now, sorry, I keep forgetting.
I was just going to ask if you could send us this or share us this file.
Yeah, so I'm going to just export this as an HTML, and I'll put it, and then next week we'll continue working on it, and then I'll try and put it on again. Just send me an email if I forget to do it. Okay, so you can just see these steps. Okay, so I've chosen these two tests because, as I said in that paper, it showed it's the majority of tests being done in public health journals. Okay, so you can already do most of the things, and you can do it properly now. Okay, any other questions, comments, concerns? Because I'm going to let you go. Okay, let me just take attendance because, again, there's going to be people who miss out on this, and you know, if you miss out on this, you've really missed out. Okay, let me save this so it doesn't go away. Okay, file, close folder, editor, file, close folder, code, quit code. Okay, I've done it in the right order.